Could you call people in, maybe?
Welcome everyone to the first afternoon session of this amazing workshop. So our first speaker is Tat Lam, and he's going to talk about modulated symmetry and LSM anomaly.
Thank you so much. So first of all, I would like to thank the organizer for the opportunity to speak. And as some of you may know, that my talk was originally scheduled to be given online. Given remotely because of visa issues, but fortunately everything was sorted out in the last minute, so I'm really glad that I'm here. So today I'm going to tell you something about modulated symmetries and LSM anomalies from a SymTFT perspective. And this is work done in collaborations with two fantastic collaborators, so Sal and Omer. They are both based at MIT. And Sal is here in the audience, sitting right there. And and he also gave a poster about another work that we've done in collaborations also with Omer and Guy. So that's closely related to what I'm going to talk about. And if you haven't seen the poster, definitely check it out. Okay? Good. So first, what is this talk going to be about? So in this talk, we're going to explore the interplay between internal and space-time symmetries. Okay? And I'm going to discuss two kinds of instances. So one is modulated symmetries. This can be thought of as an interplay between internal and space-time symmetries. Then I'll discuss also LSM anomalies. This has been discussed a lot in the literatures, and this can be thought of as a mixed anomaly between internal and space-time symmetries. Then I would like to discuss a proposal towards incorporating space-time symmetry into a framework of symmetry TFT. And the idea is to replace symmetry TFT by the notion of space-time symmetry enriched topological orders. And we will see example of this. And then using this symmetry TFT, we will be able to analyze various dualities and various discrete gaugings in the presence of space-time symmetries. And in particular, we'll see that in some cases, modulated symmetries and LSM anomalies could be related by discrete gauging. Okay? And in the talk, I'll try to discuss both Hamiltonian lattice models and Euclidean field theories. Hopefully that will reduce some barriers in terms of language barriers. Okay, so now let me begin with some high-level conceptual points, and then we'll narrow down to more specific examples. So usually when we think about symmetries, we think about them as two classes. One is internal symmetries. So these are symmetries that act on internal degrees of freedoms without changing the space-time coordinates. On the other hand, there's also space-time symmetries, which are symmetries that change the space-time coordinates, for example, doing translations. So generally, they can form some non-trivial group extensions. And because internal symmetries composed with internal symmetries always give us internal symmetries, so that means that internal symmetries should always be a normal subgroup. So this is the group extensions that can be formed by internal symmetry and space-time symmetry. But more generally, we can replace these internal symmetries by some higher form symmetry or non-invariable symmetries. And a similar structure should also exist there. But generally, if we are some particle physicists, we usually deal with relativistic field theories. And in that case, there are strong constraints on a possible mixing between internal and space-time symmetries due to Coleman-Mandrula theorems, which says that any internal Lie group symmetries should form direct products with the Poincare symmetries. So it imposes a very strong constraints on a possible mixing between internal and space-time symmetries. However, in the case of non-relativistic field theories, and also in lattice models, which I'm going to talk about, that this kind of non-trivial extensions can exist in a ubiquitous way. And I hope that I will be able to convince you that even in some very standard models, there are already this kind of non-trivial mixing between internal and space-time symmetries. Okay? So let me begin with one kind of this kind of mixing. This is a particular kind of mixing, which I'll call modulated symmetries. So what is modulated symmetries? So modulated symmetries are internal symmetries that have, its symmetry actions has a non-trivial spatial modulations. So usually when we think about symmetries, it acts uniformly in space. But for general symmetries, they can have actions that are changing as we move in space, okay? So because their actions are not uniform in space, so that means that they wouldn't commute with the space-time symmetries. In particular, that means that space-time symmetry will generate some actions on internal symmetries, and that means that internal symmetry and space-time symmetry form some semi-direct products. And these actions will be captured by a group homomorphisms from space-time symmetry to the auto-automorphism group, to the automorphism group of the internal symmetry. So this notion summarizes and generalizes a large class of symmetries that has already been discussed in literature. So one is Lifshitz field theories. So Lifshitz field theories is an example of non-relativist field theories where the time direction and space direction behave differently. So in time direction, we just have a standard time derivative, but in space directions, we have a partial x squared phi squared. So as a consequence, that means that the symmetry that acts on phi involves shifting phi by constant and shifting phi by the function linear in x. So because there's a linear in x transformations, so this is an example of modulated symmetries. And the symmetry generators will form some non-trivial algebras with the momentum operators. So another example that has been discussed in the literature is what's called exponential symmetries. And this is defined on lattice models. So for people who are less familiar with lattice models, let me just go through the setup slowly. So I'm going to work with 1 plus 1D spin chains, and on every side, there's a Zn qubits. So Zn qubit just means that there's an n-dimensional Hilbert space at that side. And on this n-dimensional Hilbert space, we label the states by group elements in Zn, and then we can define a clock and shift operators, okay? And the important thing is that this clock and shift operators are generalizations of Pauli operators. So this Z and X in particular do not commute. And their non-commutativity is captured by the Zn nth root of unity. Okay, so now we're going to use this Z and X operator to build some lattice models. So the model that we want to build is a close avatar of the clock models. The Zn clock model is the generalizations of the Ising models, and now I'm going to do a further generalizations. So if this coefficient A is said to be 1, this is just a Zn clock model, which involve the Z and Z dagger couplings of nearest neighbor sites. And there's also a transverse field term. But now let me allow to put in this factor of A that change the coupling here, okay? So this A I required to be coprimed to N. So this simple modifications already change the symmetry structures dramatically. So first, let's review what happens when A equals to 1. When A equals to 1, we get a Zn clock model. And in that case, the symmetry is just given by product of X. And this is uniform symmetry. It commutes with translations. So the total symmetry group is given by Zn tensor products with translation, which is captured by Z. On the other hand, if we have a non-zero A, then the symmetry becomes a very different symmetries. So it's a symmetry that's given by product of X to the power A to the power J. So the exponent that appears in the definition of this operators already is a non-trivial functions that depends on the positions. So as a result, translation acts non-trivially on this kind of symmetries, and they form semi-direct products. So in particular, if we do a translations, the symmetry will be mapped to its 8th power, okay? So that's why there's a semi-direct products. Good. So let me now make some general comments about what's the feature of this kind of modulated symmetries, and then it just follows from the fact that translation mixed with internal symmetries. So first of all, modulated symmetries generically will be broken, explicitly broken by periodic boundary conditions, and as a result, if they are spontaneously broken, they will lead to system size dependent ground state degeneracies. So let's do this example that we have discussed before. So let's now imagine that we put these systems on a periodic closed chain, okay? And it has a number of sides that's given by L. So we now just take the symmetry that exists on the infinite chain, and then we just truncate it and put it on our systems and ask what happens. So this is a symmetry operators that is the truncated versions, and here this side is identified with this side. So that's why here we have x1 to the power A, and here we have x1 to the power A. So the important thing is that this symmetry operators that the truncated symmetry operators commutes with the Hamiltonian at most of the side except at this last side. And this is because we are working with these periodic boundary conditions. And the non-commutativity is given by this non-trivial phase, and that is proportional to omega to the A to the power L minus 1, okay? And this has an important consequence. So that tells us that generically, the symmetry, the Zn symmetry that we start with on infinite chain will be broken on a closed chain. And this breaking there can still be some residual symmetry that survive. And in this case, if we raise the symmetry operators to power k, n over k, where k is given by GCD al minus 1 comma n, then we can trivialize this phase. And that means that we have a zk subgroup symmetry that survive. And that's generated by this u to the power n minus k. Okay, but this thing might sound very bizarre, that how can a symmetry be broken by a periodic boundary conditions? But now let me just draw an analogy between this with something that we are very familiar with. So let's try to interpret that the change of system size as inserting a translation defect. Okay, so this is really a leap of faith. Okay, but now there's something that we're very familiar with. Suppose we have a non-abelian symmetries. If we insert a symmetry defects, then the existence of symmetry defects will break the symmetry down to a centralizer of the symmetry defect. And in this case, we are inserting a translation defect, and this will break the internal symmetry down to centralizers. So this might remind people of this notion of crystalline equivalence principles, which says that internal symmetry, space-time symmetry can sometimes be treated as internal symmetries when it comes to classification of SPT phases. Okay, so this is a very generic phenomenon that symmetry will be explicitly broken by periodic boundary conditions. So the next things I would like to discuss is that when we have symmetries, we also will not only define symmetry operators that commute with Hamiltonians, we also define topological defects. So what are topological defects? Topological defects can be thought of as some local modification of the Hamiltonians, and they're topological in the sense that they can move by local unitaries. But in this case, if we have a modulated symmetries, what happens is that the symmetry defect of a modulated symmetries are topological, but they do not commute with translations. So the precise word to say is that they are topological in the sense that when you move operator from one side to the other side, you need to go through a non-trivial twist by automorphisms. So this is very much similar to boost symmetries, which defines a topological defect. However, it doesn't commute with Hamiltonians. So let's again do the examples in our generalized clock models. In our generalized clock models, we can imagine that we want to insert some symmetry defect here. So what we'll do is that we'll just apply symmetry transformation at this half of the space-time, okay? So when we do that, we'll generate a phase sitting in front of these terms that couple these two sides, but then the rest of the terms will remain untouched. So this can be thought of as a local modifications of the Hamiltonians. So now we can move these defects just by undoing some of the symmetry transformations, and we can move it to somewhere else. So we can move this defect to here. So what happens is that when we do move this defect from here to here, we see that the phase that we obtain is a different phase now. So when a equals to 1, there will be the same phase. So that means that the defect that we obtain is the translation counterpart of the original defects. But now, because there's this non-trivial A dependence, then that means that the defect that we obtain is not the translated counterpart of the previous defect. And this can be thought of as the symmetry defects being permuted when we move it. Okay, so these are the general features of these modulated symmetries. So now, let me now turn to talk about space-time symmetry in symmetry TFT. So in this conference, we have seen a lot of talks about symmetry TFTs, and it's a very natural framework for characterizing symmetries using topological field theories in one higher dimensions. So one very natural question one we ask is that, can we formulate symmetry TFT for these modulated symmetries? But this is really behind more bigger questions, because modulated symmetries involve a mixing between space-time symmetry and internal symmetries. So this requires us to incorporate space-time symmetries into a framework of symmetry TFT. So we gave proposals. So the proposal is that we want to replace symmetry TFT by space-time symmetry enriched symmetry topological field theories. So the idea is very simple. The idea is that the most general group, a symmetry group that we have, involve a mixing between internal symmetry and space-time symmetries. And now suppose we have some theories that has some anomalies of this total group. Then we just put this series on the boundary of the GSPT in one higher dimensions that cancels the anomalies. Then we just gauge this internal symmetries. Notice that internal symmetry is always a normal subgroup. So gauging these symmetries wouldn't change the space-time symmetries. So the thing that we get is a topological field theories that is just obtained by gauging the internal symmetries. But then importantly, there is some data that left behind that is the enrichment of the space-time symmetry to the symmetry TFT. Okay? So let me just say some general philosophy about why we want to think about this. So one very naive thing is that one might want to do is that one might also want to gauge space-time symmetries. so that everything will just be inconsistent. So in this case, I'm putting space-time symmetry and internal symmetry at different footings. And the reason why I do that is because first, I don't know how to gauge space-time symmetries in general. And second, for most practical purpose, we don't need to gauge space-time symmetries. So this is what we propose here is sufficient to capture the physics that we need. Okay, and one important remark is that now, because I have this space-time symmetry enrichment, and this enrichment generally breaks the topological properties of the symmetry TFT. So that's a feature, but not a bug. So we'll see how things will work, even though we break some topological properties. Okay, good. So now let's talk about a concrete example of symmetry TFT for modulated symmetries. So let's just talk about the exponential symmetries that we started with, and then what is the symmetry TFT for that? So the idea is that let's start with the paramagnetic phase, and then we just imagine that on top of the systems, there's an exponential symmetries, which is an extension of 1 plus 1D symmetries to 2 plus 1D. So in this case, the symmetry is uniform in the y directions, but it can have modulations in the x directions. So if we start with this, we can gauge the symmetry. Then we get a stabilizer code. Stabilizer code is just a nickname for Hamiltonians where all of the terms commute. So in this case, the stabilizer code that we get for people who are familiar with toric code is very much similar to toric code, except that it has some little A dependence that are sitting here and here. And this actually has some drastic implications. So for example, it changed the symmetry operators that could exist in this series. So in this series, the symmetry operator that survived is something like this. It's a product of X and with a non-trivial dependence on positions. So for example, this is the operator that will create some topological anyons. And on the other hand, we can also have an operator that are made of Z. And notice one thing, that this operator has some modulations where it has an exponential function that grows to the right, and this function has an exponential function that grows to the left. So they are sort of like reflections of each other's. This will be very important later. Okay, so this is one way to get this stabilizer code or to get the symmetry TFT on the lattice. But there's actually a more transparent way to think about this kind of symmetry TFT. So the idea is the following. So notice that when I have this strings, it will create some anyons if I truncate that. And if I stop the string here, then I'll create some anyon that is roughly speaking e to the power a. But if I truncate here, it becomes e to the power a to a squared, and so on and so forth. So that means that if I move an anyon from one point to the other points in the x directions, it has to change its anyon type. So then we can interpret this as addressing ordinary Zn toric code, which is a TFT, and by some permutation defects that are perpendicular, that are foliated in the x directions. So what this permutation defect is doing is that if we have a particle E, when it moves it across, it will becomes e to the power a. On the other hand, if we have a particle m, when it moves it across, it becomes m to the power of a inverse. So it changed permutation anyon type. So notice that this anyons, if we move in this directions, it has to change anyon type, but there's no obstruction to move in the y directions. So this means that this series actually partially breaks the topological properties of the topological field theories because of this permutation defects. Okay? And importantly, to define this theories, we always need to specify a foliated structures, which is basically tell us how the permutation defects are inserted. This is a property of this kind of translation symmetry enriched TFT. Good. So this series can also be formulated using field theory language. So it turns out the field theory is something very close to something that we have seen in the past. So this is a BF-like field theories, but however it is anisotropic. So it's anisotropic in the following sense. So here, usually when we write BF theories, we will use just the standard derivatives. But in these models, we want to replace the derivative in the x directions by something that is a little bit unstandard. Okay? So we want to address it with some a. So if a equals to 1, this is just the usual difference operator in the x directions. However, we have this little a. So this changes this series in the x directions. On the other hand, t and y direction just remains the same. And in this series, then we can build symmetry operators. But because now we have a non-standard derivative in the x directions, so the operator that we build that are topological or gauge invariant will have to be made of sum of ax, but then with a coefficient that changes with x. So coefficient is given by a to the power x, and this agrees with this coefficient that's sitting here. So similarly, there's also a coefficient sitting in front of the bx operator that agrees with this. Okay? This is a filter way of thinking about this symmetry TFT. So now let me discuss one applications. So if we have a symmetry TFT, one thing that will be very useful is that we can use it to discuss gauging. So let's say we start with the rough boundary conditions, which is equivalent to setting b equals to 0. In that case, there's a symmetry that's made of a product of x with certain modulations. And the Hamiltonian that commutes with the symmetry is the one that we have already constructed. And now let's say we want to gauge the symmetry. So to gauge symmetry in symmetry TFT means that we want to change the boundary conditions. So we want to change the boundary condition from rough to smooth. And in that case, we'll set the gauge field A to be 0. And in that case, the symmetry that we obtain is made of this Z, okay? And this Z, notice that has a different modulations. It's sort of like reflections of the original symmetry that we have. And also, the Hamiltonian that we get from gauging is sort of the reflected versions of the original Hamiltonians. And of course, we also have a change of basis. So what this is telling us is that even if we set h equals to 1, we don't have the Kramers-Wiener duality, which is implemented by gauging, is actually not the symmetry of these models. But rather, we can combine this gauging procedure or this Kramers-Wiener duality with reflections to make a non-invariable reflection symmetries. And it turns out that this non-invariable reflection symmetry is also anomalous. So we can use it to constrain the critical points at h equals to 1. So this is one applications. Oh, and let me also mention that here I only talk about specific models, but in South's posters, we also discuss a more general generalization. In fact, there's a large family of models that generalizes this clock models, which always have non-invariable reflection symmetries. And notice that in those models, Kramers-Wiener is never symmetries because the models break reflections. So you always need to combine Kramers-Wiener with reflections to make a proper symmetries. Okay. So now let me move on to talk about LSM anomalies. So this is an anomaly between space-time symmetry and internal symmetries. And let me just do an example. So in 1 plus 1D, we can imagine that we have a Hamiltonian of this type, which is usually called XY models. And in this case, let's just focus on two symmetries. So one is a symmetry made of product of X, the other is symmetry made of product of Z. So in this case, one important thing is that even though these two symmetry are linearly even though this symmetry is just form Z2 times Z2 symmetry group, but then they actually act projectively on a local Hilbert space. What I mean that they act projectively on a local Hilbert space is that, imagine that I just truncate the symmetry to be on one side. So this is made of X, this is made of Z, but we know that X and Z do not commute. So that's why local Hilbert space is in projective representations in the Zn times Zn symmetry. And as a result, then that means that if we put the system on a closed chain with a system size L, then these two symmetries do not commute. And their non-commutivity is captured by a phase that is proportional to L. So this, again, we can interpret this as some kind of anomaly that's similar to A1 cup A2 cup A3 type of anomaly. And if we interpret change of L as an insertion of translation defect. So recall that in the case of A1 cup, A2 cup, A3 anomalies, if we insert a symmetry defect for A1, the A2 and A3 symmetries will actually not commute, and their non-commutivity is controlled by the defects. Okay, so the reason why this is called anomaly is also because that it is an abstraction to trivially gap phase and also translation preserving gauging. So it's a very useful result. If we find the LSM anomaly, we know that something must be non-trivial in the inferent. Good. So now let's try to construct the symmetry TFT for this LSM anomalies. So the idea to start is that let's just first look for SPT that cancel the LSM anomaly. So what are SPT that cancel LSM anomaly? It turns out this is given by this so-called weak SPT. So weak SPT are SPT protected by internal symmetry and translation symmetries. So in this particular case, we can consider a 2 plus 1D weak SPT, which can be thought of as an array of 1 plus 1D Zn times Zn cluster chain, or 1 plus 1D SPTs that are stacked in the directions perpendicular to X directions. And this things importantly is a SPT protected by internal symmetry and translation symmetry. Because if there were no translation symmetries, we can just group a copy of cluster chains and then group them together and annihilate them. But in this case, because there's a translation symmetry, so that grouping is forbidden because that breaks translation symmetries. So here on each chain, we have a Zn times Zn cluster chain. So these are the stabilizer that describe this Zn times Zn cluster chain. And at every size, there are 2 Zn qubits, and then they have their corresponding X and Z operator, and also X tilde and Z tilde operators. So in a field theory language, we can describe this kind of weak SPT as A1 wedge A2 wedge EX, where EX is a form that is proportional to DX. So its sole purpose is to make sure that everything that depends on A1 and A2 are just the time component and the Y components of A1 and A2. So it's like inserting really like an array of a cluster chain, okay? And one important thing is that if we now cut open these boundaries, then because there's a cluster chain, and we know that at the boundary of a cluster chain, or Zn times Zn SPT, there's always a Zn times Zn projective representations. So that means that on the boundary here, we always get a Zn times Zn projective representations that agrees with the LSM anomaly that we talked about before. So this is really SPT that cancel the LSM anomaly. So now we just proceed with the idea we had before. So let's start with the weak SPT, and let's just gauge. So if we gauge the Z2 times Z2 symmetry, the Zn times Zn symmetry, then we get a stabilizer code of this type. And so the ground state of this stabilizer code will be the symmetry TFT. And now let's ask, what is the symmetry in this series? So symmetry in this series, or the string that creates anyons, first of all, involves these things that are made of product of Z tilde. So we can just think of it as creating an anyon that is E tilde. On the other hand, there's another kind of strings that is made of product of Z, which is a uniform product of Z. On the other hand, it's also a product of Z tilde, which is a linear function in X, okay? And we'll call anyons created by this E. So in this case, one important thing we notice is that because there's this non-trivial modulations, so if we do translations on this string operators, that actually generates the string operator of E tilde type. So that means that this kind of symmetry actually is form of modulated symmetries, and this is exactly the same modulated symmetry as the dipole symmetry. So there are similar stories for the symmetry operator for X and X tilde. Okay. So the fact that these operators are modulated actually tells us that we can also think of this kind of stabilizer code as some kind of translation symmetry enriched versions of Zn times Zn toric code. So we'll just add some permutation defects, and its sole purpose is to bring E tilde, if we have E tilde to bring across the permutation defect, it just becomes E tilde. But if we bring E past the permutation defect, it will generate the E tilde. Because this E has this non-trivial modulations, that's why it will generate E tilde here. So there's a similar stories for the M particles that if you bring them across, they also generate the other type. So this is a way to think about this symmetry, think about this stabilizer as a symmetry enriched toric code. So it turns out that this series can also formulate it as some gauge theories or field theories. So notice that I mentioned before that the symmetry here forms some kind of dipole symmetries. So it's very natural that the theory underlying them is some kind of gauge theories for dipole symmetries. But dipole symmetry couples to usually some kind of tensor gauge fields, where the tensor gauge fields have some non-trivial gauge transformations. For example, AXX will have a gauge transformations that is given by partial x squared phi alpha, while in the other directions it's just a standard gauge transformations. So we can build a BF theory using the same set of fields A and B, and then they will give us this dipole gauge theories. And we can also build the symmetry defects, and then they match with the lattice result. And in particular, notice that one of the symmetry defect will have non-trivial x dependence, while the other doesn't have x dependence. Okay. So now we can use it we can use this symmetry TFT to do two things. One is that let's just consider boundary conditions which recover the LSM symmetries. So the boundary condition that recovers LSM symmetries is the smooth boundary condition for X and Z qubits, a rough boundary condition for X tilde and Z tilde qubits. Okay? So in the field theory language, that means that we want to introduce some boundary degrees of freedoms, which I call AX and BX, and then this is the boundary condition that we want to impose. So now if we look at these boundary conditions, it's easy to figure out the symmetries. So the symmetry turns out one of them is made of product of Z, the other is made of product of X, but with some X tilde that's stressed on them. So then it's easy to check that these two things don't commute, and their non-commutativity is given by omega to the L. So this really recovers the LSM anomaly. And now using this boundary condition, it's actually very easy to prove the LSM theorems. So this is just to do a consistency check. So what is the LSM theorem? LSM theorem is saying that if we have a symmetry that has LSM anomaly, then there should be no translation preserving gap SPTs. So in the language of symmetry TFT, if we want to build SPT, what we want is that we want to pick boundary conditions on the other side, which is on the physical side, and where we want to condense the E and M tilde particles. But notice that E and M tilde particles are modulated. So whenever we move them past the permutation defect, they will generate other particles. So that means that we cannot condense them without breaking translation symmetries. So that's a sort of a one-line proof of LSM theorems. Of course, we use this symmetry TFT. And then the other thing is that you can also consider boundary condition, which is a smooth boundary conditions for all of the qubits. And in that case, it is equivalent to gauging the Zn subgroup of LSM anomalies. So this boundary condition just amounts to set the B field to be 0 completely. And in that case, the symmetry that survive on the boundaries involve a product of Z tilde, which is uniform, and this kind of symmetries, which is modulated. And they form a non-trivial algebra that's given by dipole symmetries. So what we have learned here is actually a statement that if we gauge one of the Zn symmetry and LSM anomalies, we actually get the dipole symmetries. So in that sense, LSM anomaly and dipole symmetries, they're just two sides of the same coin. Okay, so let me now conclude. So in this talk, we have discussed symmetry TFT and dualities for 1+1D symmetries involve translations. In particular, we discussed the case of modulated symmetries and also LSM anomalies. And of course, there are several directions one would want to take. So one thing is that we have this very powerful framework of describing symmetries using categories. What about spacetime symmetries? Can we connect spacetime symmetries with this categorical framework? The other thing is I'm only talking about 1+1 stories. What about higher dimensional generalizations? In higher dimension, we have rotations. Does it change your story? And the other thing is, I think it's also very interesting, is that I discussed there's this large family of spin chains which have modulated symmetries. And of course, one thing, and also in some cases, there are anomalies at a critical point, sorry, at the self-trivial points that forbid the theory to flow to some trivial gap phase. Then one interesting thing is it possible that the theory will flow to some critical point, or it's just a first order phase transition? And if it's a critical point, then maybe there's a chance that we would see some criticality that's beyond CFT. So that's something we are work in progress. We're doing numerics now. Okay. So let me conclude and just to say that there are many more to explore in space-time symmetry. Thank you.
Questions?
I have a question about the second last point. So I think a natural candidate is to look at the parafermion theory, like ZK parafermion CFT that has self-duality on D2 gauging. And there are spinning operators with spin that commutes with this category. So if you turn on those operators, you are of course not going to get vanilla, familiar faces.
Oh, okay. That's interesting.
That's my guess that it could lead to one of your, it will be the continuing version of your spin chain with modulated symmetry.
Yeah. So you want to turn on some operator that has
with spin.
Yeah. That's an interesting thing to do. Yeah.
We can talk about after.
Yeah, that's very interesting. Oh.
Good question.
Good question. So in your proposal for the SymTFT for space-time symmetries, do you have in mind only the lattice case or also the continuum field theory case?
That's a very good question. So far we're doing it on lattice because we're doing translations. So I don't know what happens in continuum. But some of the field theory that we wrote down can take continuum limits. So I think we're halfway there. So yeah, there's some hints. Maybe there's some way we can formulate in continuum.
Thanks.
So you said that you could get to the dipole symmetries by gauging. Can you also gauge it back and get rid of the dipole symmetries?
Yes, that's right. Yeah. So it's just like symmetry TFT, right? We can change boundary conditions. Yeah.
But this is for a discrete case. Now, when you have the continuum dipole symmetry, you cannot do this map to the LSM anomaly, or can you? Like the ones of the Lifshitz scalar, for example, you do the same things with a lot of X derivatives. No?
Oh, okay. If you have U1, if you gauge the Zn subgroup, I think you can still get the
Zn subgroup, yeah, okay.
Yeah, maybe. Yeah.
But this is the way to do it for the full symmetry, because people were very confused about how you actually describe this, put background fields for this kind of symmetries, at least once. I don't know if now it's understood.
Oh, well, you mean the
Higher dipole algebras, yes.
Oh, I see. I think the same story for U1 and SymTFT would hold in this case.
Okay.
We just replace them by U1 gauge fields, and then we add this real gauge fields to constrain them.
Okay, okay.
That should work.
More questions? There's none. Let's thanks Scott again.